Assalamualaikum. My name is Dato' Muhammad Iskandar bin Dato' Muhammad Ayub. Welcome to our group presentation. We are group 4 from section 1. And today we are excited to introduce you to our project, which is focusing on critical aspect of industrial process water level control in cooling system, cooling tower using PID control. Okay, let's start by understanding the basics. As you can see on the left of the slide, a cooling tower fundamentally removes heat by allowing hot water to contact dry air, causing the water to evaporate and cool down. This is a crucial process in many industrial settings. To ensure this process operates efficiently, a robust feedback control system is essential. Such a system helps maintain key variables like the temperature, level and flow rates, leading to inefficient operation. Now, why is this important for our project? Well, in this project, water level is our main focus. Why? Because accurate water level control directly impact energy efficiency and help prevent common issues like pump damage and overflow during the process cooling. Moving to the right slide of the slide, you will see how we plan to achieve this. The PID control system or proportional integral derivative control is what we will be utilizing. This powerful control method works by continuously adjusting actuators such as pump and valve based on real-time sensor feedback with a goal of minimizing any error from our desired set point. By implementing PID, the variable speed driver, we anticipate significant improvement. This approach will enhance overall performance, reduce energy consumption and lower maintenance costs by allowing motor to run much more efficiently, only using the power truly needed. Finally, it would nothing the broad applicability of PID control. It not just for cooling tower, the application of PID control is widespread across the various industry for controlling critical parameters like temperature, flow, pressure and level in diverse systems such as furnace, pipelines and large processing tank. In summary, our project delves into optimizing cooling tower operation through precise water level control using the highly effective PID system. Okay, now let's look at the heart of our control system, the feedback loop. This block diagram visually represents how we will maintain the desired water level in our cooling tower or water tank. First thing is the set point. On the far left, you can see the set point. This is our desired water level. Think of it as the target level we want the water in the cooling system to always maintain. It's the ideal state we are aiming for. Second is the error calculation. The circle immediately after the set point is where the magic feedback begins. Here we calculate the error. This error is simply the difference between our set point, which is what we want, and the actual level measured by the sensor and what we currently have. If there is difference, it means we need to make an adjustment. Number 3 is the PID controller. This is the brain of our operation. The PID controller takes the error signal at its input based on the size and duration of the error as well as the rate at which the error is changing. The PID controller calculates a precise output signal. This output is designed to bring the actual level as close as possible to the set point. It's constantly working to eliminate the error. Number 4 is our control valve. The output from the PID controller then goes to the control valve. This valve is our actuator. It device that physically regulates the flow of water into or out of the cooling system. If the PID control determines the water level is low, it will send a signal to open the valve more, allowing more water in. If there is too high, it will signal the valve to close, reducing the water inflow. Number 5 is the cooling water tank. This is cooling water. or water tank itself, the process we are trying to control. The control valve directly influence the water level within this tank. And number six is fine. And number six is sensor. This component is crucial for feedback. It continuously measure the actual water level inside the cooling tower. This measurement is then sent back to the beginning of the loop to be compared with our set point. That's all for the block diagram.
Assalamualaikum and very good day to everyone. And today I will discuss about our result and analysis. And this page is about proportional result. So basically, the value of proportional result, we put the gain, which is 1, and we got the initial process value, which is 15, and the final settled process value will be 37.5, with the rise time around 5.5, settling time 19, and with steady state error 12.5, because we don't set an integral time, right? Okay, let's move on to the next result analysis, which is PI. We call it as proportional and integral. The control type is PI with the set point 50, and the proportional gain will be 1 with the time set, which is 0.01 minutes, or basically 6 seconds. The initial process value approximate around 30. Final settled process value will be 50, with the rise time 12 times units, settling times 47 times, and steady state error it's 0, because we got in our graph here the result on the LSV, which is the water tank inside. We got the steady state error, which is on the set point, and LCV, we got same exact line, which is we can state as no error state, and we got the final that process will be 0. And the final our final result and analysis, which is using PID, proportional, integrate, and derivative. We uh, set point, which is the same 50, with the proportional gain 1, integral time 0.01 minutes, derivative time will be 0.01 minutes, and initial process value at start will be 30, which is around in the graph 30, and initial process, I mean the final step process will be 50, and the rise time, which is 9, settling time, which is 24, with the steady state error 0. It's the same as PI. We can provide less error, but this one we got 0 because our graph at LCV, which is the water tank, we got same line at set point. All right, that's all for me. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Al-Kawarizmi bin Willy. So I will present or explain about discussion. So what this study about? This project is about a PID control in a simulated water tank or cooler tank to regulate water level by analyzing PID, and PI configuration. So as we can see here, for the P, control had a fast response. The rest time is 5.5 units, but it was inaccurate. It stabilized at 37.5 instead of 50, with a steady state error of 12.5. So with PI. PI is proportional integral. Its control improve accuracy and reach the set point with zero steady state error, but had a slower response rise time, which is 12 unit. The settling time is 47 unit. And PID, when the PID is applied to the water level, uh, its control achieve the best balance rise time of unit, settling time of 24 units, and no steady state error. So the derivative component in PID help predict and reduce future error, improving both stability and responsiveness. The LabVIEW is a software that used to simulate a closed loop system providing real-time monitoring and control of PID parameters. The simulation environment closely resemble real industrial system such as water level and temperature control. And the last one, the lab demonstrated that PID tuning is critical to achieve optimal system performance, with PID control being the most effective overall. So that's all from me. I will pass to the next presenter.
Hello, hi, assalamualaikum warahmatullahi wabarakatuh. My name Hilmi Iskandar Bisaipu Bahri, number CN230435. So today I want to present about the conclusion for the all project. So the first one is the role of the PNID in cooling tower system. Okay, the rule is the maintain decide water temperature by adjusting fan speed or the valve position, balancing the proportional P, integral I, and the derivative D action to ensure the stability, efficiency, and responsive for our project. And second, comparison of the control. So control 1, KC is 1, TI is 6 second, TD is the 6 second, is the response yet the stable with the balance error correction and damping in charge by the absence of the dead time or load, making it outperform control 2 in stable stability and efficiency in the contract. For the control 2, KC is 0.2, TI is 12 second, and TD is 12 second. Is to conservative with slow reaction per set point tracking and extended setting time, limiting it effectiveness. Control 1 is the better choice through features optimization full in charge its performance.